So, good morning everyone and back to the class on tribology. So, one of your friend told that we were dealing with module 4 in the last class. What was the title of the module 4? Can anyone let me know what content we did in the last class, Chaitanya? If you won't reply, then what's the use of taking me the class then? What was the topic we were dealing?
Hydrostatic bearings.
We were dealing with hydrostatic bearings. Before that, we dealt about what you mean by hydrostatic lubrication. We brushed out the concepts and then we gave an outer view, the exact schematic diagram, how does an hydrostatic bearing works exactly. So after that, we were supposed to derive an equation for load bearing carrying capacity and the rate with which the oil is flowing. So the basic diagram related to that I had explained in the previous class. So now today we have to deal up with the derivation part and then we need to solve the numericals. So with that background, and I also explained you the types of compensating elements which are being used in hydrostatic bearings. So you have a compensating element here in which you can use which is being needed. Either you can go with capillary tube, orifice, or constant flow valve based on the requirement. So we figured out when and how to use this type of valve in our compensating element, so which will be located over here. So this basically helps to vary the pressure from the supply to that of the required pressure value, which has to be passed through the recess. So this phenomena we have explained in the last class already, right? So now all the concepts what you studied in hydrostatic bearing has to be focused now to get the derivation of load carrying capacity and the rate of oil flow. So a schematic sectional view of the same is being shown over here in the slide, right? So you will be having the thrust or the axial load which has been passing through the shaft here. So this is an sectional view of the bearing with the journal. So you can see that this part is nothing but our pocket. So you will be having a gap between the journal and the bearing. So this is the gap. So in this gap the oil will be filled out. So this is like a clearance which acts between the journal and the bearing. So the amount of thickness of the oil film, you know that it is usually represented by H. If it is H naught, that is the minimum oil film thickness which is being needed. So I told you already, hydrostatic bearing has least amount of frequency, least amount of friction, as it even runs in the speed comparatively lesser than that of hydrodynamic type of journal bearing, and hence the friction will be less. Due to the friction, we can consider a negligible amount of friction. So due to that, a very minimum thin film of the oil is also capable enough to see that the journal runs smoothly with reduced or negligible amount of friction, and at the same time it will be having a capacity to bear the weight which is being applied to it. In the same thing, we have known the concept that in case of hydrostatic bearing, the pressure which is being required is subjected through external media by using a pump. So you send the oil with required pressure. So the pressure of the oil which is there within the inlet of the oil pipe is nothing but our P naught. So based on that, if you just draw the lines here down with respect to the sectional view, you can just figure out this view. Okay, so this is just if you take the projection of these lines, so it will take the rings as shown in the figure. So further, if you get down, you can see the variation in the pressure which is found within the inlet of the pipe. Okay, so now I will just explain you the concepts. So then we go for the derivation. So this is just the, if you see from the top, so it will just be the view what it looks like. Okay, so when you view from the top, this will be your top view what it looks like basically, and it also shows you the pressure distribution. So P naught always refers for the pressure distribution of the oil which is passed through the inlet pipe. Along with that, you'll be having the radius of the journal, the bearing, and the rings which are formed due to the clearance. So you'll be having the projection of this line and the projection of this line. So this is mainly the clearance. So the projection of these two lines here, that shows the ring associated with the clearance. So the area associated with that will be nothing but our dr. And this entire curvature will provide you the length of the clearance basically. Okay, so these things you have to be knowing carefully. So now let us start with the description and which equation you use basically for starting up with the analysis to know the flow of the lubricant in the given elemental ring. So first what you have to understand is you should consider an elemental ring. So the elemental ring here is nothing but this. Okay, so this is our elemental ring. This inside one is our elemental ring. So this is the radius r from the center. So this is our elemental ring. Okay, so after knowing this, you should assume that the thickness of this ring is dr. So it is mainly dependable upon the clearance value. So based on the clearance, the thickness of this ring also varies. So if this is the radius r, so we assume the thickness of this elemental ring to be as dr. So this is the area dr for this particular elemental ring. So we are mainly focusing on the clearance part of the journal bearing because you need to know the rate of oil flow as well, right? So this is the thing what you have to understand. So once the elemental ring and its area and thickness is been defined, so then now you should be able to figure out an equation which helps you in understanding the flow of the lubricant, because you know that within the clearance value, the lubricant will be flowing. So how do you analyze the flow of the lubricant within the given elemental ring? So that will be given by the equation Q is equal to BH cube by 12 mu into variation in pressure divided by length. So dP will provide you the change in the pressure which is coming across that elemental ring. And B is the width of the slot, right? So this area B will be the width of the slot, and this width will be always told to be as equal to 2 pi r because we are taking the circumference of the ring, right? So the width of the slot will be 2 pi r. And then the thickness of the oil film. So as usual, you know that it is represented by the letter H. Along with that, you should be knowing the length of the slot. The slot is nothing but our elemental ring. So width of the slot will be 2 pi r as it is a circular ring, and the slot, the length of the slot is a nothing but dr, which has been now considered here before while explaining the concept of elemental ring. So this will be the basic equation what we will be using to determine the flow of an lubricant which is passing across the elemental ring. So it is by default BH cube by 12 mu into delta P upon L. So with this equation, we have to start up our derivation. So once this equation has been clear enough with its terminologies, so then you have to start to figure out the variation in the parameters. So now what you have to understand that L is the length L will in the direction of flow is dr. Okay, so this is done. The same thing has been explained here. So I have told you what does each parameter stands for. So these parameters now has to be substituted in the equation. I told that B is nothing but the width of the slot. So in place of B, we need to write as 2 pi r. Also, length is nothing but the slot, I told, length of the slot. So in place of L, you have to write it as dr. So the equation will change slightly. So this was the equation before. So now this equation will be slightly changed. So why it will be changed is because you are now substituting the values. So here you had B. In place of B, you will write it as 2 pi into R. So now in the equation, you can see it is 2 pi R changed. The H terminology remains the same. The thickness of the oil film, that is nothing but the minimum thickness of the oil film. So in place of H, we can write it as H naught. And hence in the equation here, in place of h, you will write it as h naught whole cube divided by 12 into mu. So that remains the same, 12 into mu. And here we had change in pressure divided by the length of the slot. So length of the slot is nothing but dr. So in place of L, you will replace it by dr. So now the equation got changed into dp by dr. So this is the new version for the flow of the fluid. What you get from the equation 1, which has been declared over here. So you are just substituting the variables to the parameters given in the equation. So once you get the new equation, later you can simplify it. So you have 2 here, 12 here. So you can simplify. So denominator, it is 2 ones are 2, 6 are 12. So here the denominator becomes 6 into mu, and numerator will be pi r into h naught cube dp by dr. So this is the equation for the flow which has been passing through the elemental ring. So from this equation, now you have to try to figure out what is the value for change in pressure. And hence you will take dP outside towards your left. So other things you will retain towards your right hand side. So dP will be equal to 6 mu dr q upon pi r h naught cube. Okay, so first you will get the equation for Q. So then you will try to get the equation for change in pressure. So dP will be equal to this. So after this, what you will do is you have to do a small variation. So what is it is you have to take this dr by r towards one side, right? So this is a variation which has been shown with respect to the thickness of the elemental ring, and the radius of the elemental ring is associated with it. So we are taking this outside. So dr upon r will be put into a single bracket. So remaining thing you will write 6 mu into q upon pi h naught cube. And here this has been assigned with negative sign. So any guesses why a negative sign is assigned? Because we usually put on a negative sign here to show that the pressure decreases as the radius of the elemental ring increases. So it is not necessary that the elemental ring remains the same. Sometimes the thickness of sometimes the oil layer or the lubricant layer, what is put forwarding, if it is more, then H naught will be more. So if H naught will be more, the value of dr will be more. So if the dr will be more, the pressure gradually reduces. So if it is very less, then it will show the negative value. So to be on safer side, always we put the sign negative over here, because the variation in the elemental ring varies as per the requirement. So based on the load applied, so based on that, you have to decide which is the minimum thickness of the oil film needed. So based on that, the elemental ring thickness could be high, yeah, more. So if it is more, obviously the pressure comes down. In that case, it will be a negative value, and hence we do put a negative value over here. So this is the second equation now, what we are getting. So this is the second equation to know the change in pressure across the elemental ring. So once this is done, we will integrate this equation. So when you integrate, so this is the equation what you integrate. So when you integrate, you will get P is equal to the constant you will keep one side. Okay, 6 mu q upon pi h naught whole cube into log of r. So you will get when you integrate dr by r. Okay, so after that, one constant term comes into picture. So after integration, you will put this as equation 3. So now, once you have integrated, always in the integration, the funda is you need to find out the value of constant also. So then only you can figure out the exact value for the pressure, which is in variation with respect to the elemental ring. So here also we do the same thing. So to know the value of C, yes. So to know the value of C, you should put some initial boundary condition. The pressure could be minimum, yeah, maximum, yeah, it could be assumed to be zero also. So based on the condition. So let us try with applying the boundary condition. So here what has been assumed is the pressure will be zero when R is equal to capital R. So what do you mean by R is equal to capital R? So here you have the elemental ring. So this is the elemental ring R, and we usually find an film thickness here for the lubricant to pass on. So if there is no lubricant at all, if there is no clearance value at all, so then this small r will be equal to the capital R. So this is the elemental ring. The upper layer of the elemental ring, it has a radius of capital R. The lower layer of a elemental ring has a radius of R. So if there is no clearance at all, means if you don't have an oil film at all, so then small r will be equal to capital R. The same condition is now being applied. So in this situation, the pressure is assumed to be zero across the oil film because there will be no oil. Since there is no oil in the inlet, there will be no pressure at all. Since there is no oil, so there will be no clearance, and hence small r will be equal to capital R. So in this situation, we will put the value of P as to be equal to 0. So the same change you will show in the equation. P value will be 0. This constant term will remain the same. So instead of log small r, we will write it as log of capital R plus C. So when you have one term equal to 0, then easily you can determine the value of C. So then you will find out what is the value of constant. So this will be equal directly to, it was negative before, now it becomes a positive value because we have taken C this side. So it will be 6 mu q upon pi h naught whole cube into log of R. So now we know the constant value for the equation of the pressure what we have integrated here from the basic equation number 2, right? So in this equation, you'll come back to this equation and you substitute the value of C what you have got. So in this part, the first part will remain the same. Only in the part C, you will be writing as 6 mu q by pi h naught cube into log of R. So now the equation gets changed into this way. Okay. So after this, what you do is you have your log R and log capital R. So this could be clubbed together. So you can write P is equal to 6 mu q by pi h naught whole cube into log of capital R by small r. So this is the common thing, what you can take as a common factor. You can put a bracket to this also. So that will hold good. It's better always to put a bracket. So it is log of capital R by R, what you are putting together, and this part you are taking as a common factor. So this will provide the equation for the pressure across the elemental ring, which basically is the clearance value in between the journal and the bearing. So once this is done, we should also try to figure out what is the value for the flow of oil, the rate of oil flow, right? So the flow of oil will be obtained from the same equation number 4. So if you equate to Q, so then you will get the remaining parameters towards your right hand side. So Q will be, if you take Q this side, so Q will be equal to P into pi h naught whole cube divided by 6 mu into log of capital R by R. So we got the equation for the flow of oil within the inlet, right? So after this, our main thing is to determine the rate of flow. So the second part you have to consider now, again applying the second boundary condition. So what is the second boundary condition? First one, we assume that the pressure is 0. The second time what we are assuming now is pressure is equal to P naught. P naught is nothing but the pressure of the oil which is passing through the inlet of the oil pipe or the oil valve. So if the pressure developed in the clearance area or the elemental ring is same as the pressure which was there within the oil inlet, so then small r will be equal to capital R naught. So this is why it is now changed from R to R naught, because the pressure is assumed to be the same as it had in the oil inlet. So based on that inlet oil pressure, the radius value here will be associated with the inlet oil pressure, and hence it is shown to be as O here. So in place of small r, you have to write as capital R suffix O. So these are the changes what you have to now put in the equation for the oil flow. So oil flow equation we have derived here. Q is equal to P pi H naught whole cube divided by 6 mu into log of capital R by small r. So in the same equation, you will write in place of P as P naught, and in place of R, you will write it as R naught, because we are assuming the pressure to be equal to the pressure within the oil pipe or the oil valve. And hence now the equation changes in this way. Pi P naught H naught whole cube. So it became P naught here divided by 6 mu into log of capital R by R naught. So this is the equation for the rate of flow, right? And also you have the same equation in our this one data handbook, which tells you in terms of diameter instead of radius of the elemental ring, and hence you have a small change here. So it will, you can use the both the equation based on the data given, right? If the values of R are given, you can go with this. If the value of D is given, D1 and D2, so then it's better to go with this equation. So this is the most commonly used equation. So where the rate of flow will be given by pi into P naught H naught whole cube divided by 6 mu into log of D2 by D1. So this above equation is called as a rate of flow. Usually they ask the derivation for rate to know the value of rate of flow of the oil in an hydrostatic bearing. So you need to draw the sketch, explain the terminologies, derive the equation for pressure as well as the flow with first boundary condition where P is assumed to be 0, where small r is equal to capital R, and second boundary condition is where the pressure P will be equal to the pressure across the oil film and R will be equal to capital R naught. So with this changes, you have to show what is the equation which has been used to determine the rate of flow. Even in the problems, they ask you to determine the rate of flow. You should be familiar with the equation and to see that which equation you need to put. Usually they give the value of D2 and D1 basically. If they give the value related to R also, you will be knowing the equation what to use. So this is done. The rate of flow. So in the derivation of load carrying capacity and the rate of oil flow, we have done with the rate of flow part. So remaining thing you have to do. What is the equation you have to use for load carrying capacity? In case of hydrodynamic journal bearing, also we had a derivation for load carrying capacity. It was a very huge one. Usually they won't ask the derivation of that part, but they give you the numericals, what we have done it. But in this case, you have the chance of giving, asking the derivation for load carrying capacity and the rate of oil flow also, right? So you should be able to derive the equations. You know, load carrying capacity is the maximum load a journal bearing can withstand, right? Or capable to withstand. So you should be knowing what is the total load carrying capacity of a journal. It mainly depends again upon the distribution of the pressure. So distribution of the pressure, how well the pressure is being distributed, is the pressure across the clearance or the elemental ring is equivalent to what pressure you need basically to withstand this heavy load. Because one thing you have to remember, in case of hydrostatic bearings, even though it works on a low speed compared to that of hydrodynamic bearing, it has the capability to withstand higher load as that of hydrodynamic with reduced friction in comparison. So this is still a better approach to using, and hence you should be knowing the equation also which is used to determine the total load carrying capacity of an hydrostatic bearing. So with this aspect of data, so now we should come to derive the equation. So it is not a new part. All the terminologies are known to you. So basically, you should understand the total load carrying capacity of an bearing, right, is usually given by the summation of two parameters. What are those? It is a sum of load supported by the central axis area, okay, and the load supported by the annular area from radius r0 to r. So you have two aspects. What is the load supported by the central axis area, which is nothing but PR. So what is the main pressure distribution, which is coming across in between the journal and the bearing? So it is above the contact area, it will be positive, and below the contact area, it will be negative. So we are speaking about above the contact area. So what is the load bearing capacity? So it mainly depends upon the pressure distribution. So in this case, always the value of P naught is held constant. What is P naught? It is nothing but the pressure within the oil valve, right? So this value will be assumed to be constant always, irrespective of the variation what we get. So if P naught has to be constant, then you should decide which is the compensating element you have to use. So in case of constant flow valve, the flow is always held constant. Means to say, if you go back to the diagram here, right? So the supply pressure which passes through compensating element will be held constant. Only PR will be varied based on the load applied. Only then the load applied in the normal direction can get balanced with the pressure which has been coming in the upward direction. So then it retains the journal bearing in equilibrium condition. So this concepts what we held in the last class, kindly keep in mind, it always helps you to solve the problems. So the same thing is being told over here also. So we were in load carrying capacity. So P naught is constant, means you have to decide which is a compensating element you have used. Okay, so this is one part. The other part is the load supported by the annular area from radius r0 to r. So what is the load carrying capacity of the annular area? So it is speaking about the elemental ring. So elemental ring, you will be having the inner radius r and the outer radius capital R, right? So in some cases, we assume small r is equal to r0. So we studied recently, right? So where r is equal to r naught. So this is the second boundary condition. So based on the second boundary condition, across the elemental area r naught to r, what is the load bearing capacity? See, this also depends upon the pressure which has been developed across the clearance value. So these two concepts plays a vital role in determining the total load carrying capacity, right? So based on that, W will be equal to P naught pi R naught whole square. So this will be one part which takes place with respect to the circumference of the journal bearing, plus, so this is with respect to the elemental area. So you will be having the elemental slot width as well as the thickness. So elemental width of the slot will be given by 2 pi r, and elemental thickness of the elemental ring will be given by TR, and the pressure associated in the elemental ring will be P into 2 pi r into dr. So this will vary in between r and r naught. This is small r actually, this is capital R. So in between small r and capital R, that is the elemental thickness. If you see in the diagram over here, so this is small r and this is the capital R. In between small r to capital R, this is our elemental ring, basically the clearance part, right? So in second boundary condition, we assume small r is equal to r naught. So same thing has been shown over here. So you integrate from r naught to r as per the second boundary condition. This one. So where the pressure will be held constant. So once you achieve this equation, what you have to do is you have to substitute the value of for P. So you have the value of P which has been derived earlier, right? So we have the value of P, what we have calculated based on the boundary condition. So you have to substitute the value of P in the equation. So P naught will remain the same. You will not do any change. So this part will remain the same. P naught will remain the same. Pi will remain the same. R naught square will remain the same. Only thing we get the values changed in the elemental area, which has been elemental ring, which has been integrated from R naught to R. So in that you have to substitute the value for P. So P equation we have derived from equation number 4. So please go back to equation number 4. So what is the value of P in equation number 4? This one, as I told you, P is equal to 6 mu cube by pi h naught whole cube into log of R by R. So this value now we are going to substitute in the load carrying capacity equation. So in place of P, you will write 6 mu cube divided by pi h naught cube into log of capital R by small r. This is entirely the p value. So after you substitute the p value, the remaining part you will write the same. So 2 will be the same, pi will be the same, r will be the same into dr. So now after writing this, we will slightly simplify. So this remains the same. The integration value will also be the same, right? So only the change is here. Here you have 6 and 2. Just they take these two together. 6 into 2, it will become 12. So mu will be the same, q divided by h naught whole cube, right? So then this pi gets cancelled with pi. So in the denominator, you will not be writing pi value here. Only thing it is 6 2s are 12 into mu q divided by h naught whole cube. After this, we have the log parameter. So log of capital R by small r. You can write this in the bracket also. So remaining part is 2 has gone, pi has gone. So remaining part is r and dr. So this is how you have simplified the second part associated with the elemental ring. So after this, you will integrate this equation. So after integrating this equation between R naught to R, what you will do is you will substitute the value of Q. So here the value of Q is not substituted. Don't substitute the value of Q before integration. First you integrate. After integrating, you will substitute the value of Q. So Q is been derived in equation number 6. So this is the equation for Q. So after integrating, you will directly substitute in place of Q this equation, which is nothing but our rate of flow. So once you substitute and simplify, finally this is the equation what we get in terms of R and R naught. As we got the equation for Q in terms of R and R naught previously for rate of flow, even here you will get the equation for the load carrying capacity in terms of R and R naught only. But in the data handbook, it is represented with respect to D1 and D2. So we will change this accordingly as D1 for R naught, and for R it will be D2. So this will become D2 square minus D1 square divided by log of D2 upon D1. So wherever you have R naught, that you will consider as D1, and wherever you have R, you will consider as D2. As we did for the case of rate of flow equation, the same thing we will make the change for load carrying capacity also. So this will be the equation what you will use now from hereafter to solve the problem. Usually they ask to determine the load carrying capacity of a given hydrostatic bearing. So you should be able to use this equation. Along with that, they might ask you to determine the rate of flow. So then you should be able to find out the value of Q as per using this equation. So this is how you have to derive. And apart from that, in the problems, they ask you to determine the power loss, which usually comes across due to friction. Even though I told in case of hydrostatic journal bearing, the friction value is comparatively less, but there will be a small value of friction. So due to that friction, what is the power loss? So that also you should be able to figure out. So you have a small derivation for power loss also. Usually we use the equation for power to be as 2 pi nt divided by 60 into 1000. The same thing we use over here. After writing this equation, you should make a small change. Here we are focusing due to the friction. So in writing only T, so you will be writing as T suffix M. So whereas this will show you the frictional torque associated. Okay, so you will make a light minor change to the equation from the regular one. So you will write power loss due to friction. So here you will write frictional torque instead of just torque value, right? So it will be like frictional torque, but you should be knowing what is the value of frictional torque also. Here you cannot blindly integrate to any range. You should be knowing to what range you need to integrate. So you have to integrate to the same values what you did in case of work loading, capacity, as well as the rate of flow. So we integrated usually in between the integrals R0 to R across our elemental ring. The same thing has to be followed over here. Here also we do integrate from R0 to R. So what is the changes we are getting with respect to the frictional torque? So that will be evaluated. So this is the equation what we use to integrate for the frictional torque. So then later you will get the value of frictional torque is equal to tau into dA. So dA will be the area which will speak with respect to our elemental ring. And as dA will be given by 2 pi r, which is the width of the elemental ring, and dr is the thickness of the elemental ring. So this will provide the variation in the area of the elemental ring what we are considering. And similarly, here tau will be equal to mu into u by h. So here the shear stress which has been induced will be equal to the viscosity of the lubricant film. The viscosity value usually that will be given in the numerical problems, and u will be the velocity with which the journal bearing is revolving, and h will be nothing but the oil film thickness, right? So the same part now you can substitute in place of tau and elemental area dA. So in place of tau, you can write it as mu into u by h. And in place of dA, you can write it as 2 pi r into dr, right? So now this is the substitution what we write. And apart from that, we have one more equation to find out the velocity with which the journal bearing is moving. So that we have used already also. So it is like 2 pi r into n upon 60. So this is the equation we will use. So once you figure out this, so then you will come back to the equation number 8. So this is our equation number 8, right? So you will substitute this equation number 8 with all the values. So how will you substitute? So this was the equation number 8. So in this, you should substitute the values. So you now have the value for variation in the frictional torque value, which is mu u by h into 2 pi r into dr. So you will substitute the same over here in the equation number 8. So it gets changed in this way. But we need only the frictional torque. So you will take this delta towards your right hand side. And as it will be just differentiation is now being integrated, right? So you will remove this d. So it will be now integrated. So frictional torque will be equal to, you will integrate from the limits of the elemental ring small r to capital R. Your small r is assumed to be R0, and hence it is R0 to R is the limit for the integral, and remaining thing remains the same. Just bring out this numerical value in the beginning and write the remaining part. So it is 4 into mu pi square r cube n divided by 60h into dr, right? So later, after integration and simplification, you will be getting this value. So if they ask you to determine the frictional torque, so this will be always equal to mu into pi square into n divided by 60h into r to the power of 4 minus r naught to the power of 4. So this will be the frictional torque value. Once the frictional torque value is obtained, so then we can go for then we can go for identifying the equation for power loss due to friction. So power loss due to friction can be represented by P suffix mu. So mu stands for friction. So power loss due to the friction force. Okay, so that will be equal to, we had the equation for power, right? If you go back, see, it was 2 pi n into Tm upon 60 into 100. So you will use the same equation. Only thing, you will substitute the value of the frictional force. Frictional force you have derived here. So this value has to be substituted in the equation number 7. So this part will remain the same, only the frictional value will get changed. So the frictional torque value you will substitute, and hence this equation will be changed. After this, in place of RPM, with what it has been revolving, it is usually in RPM, right? So if we need to convert that into RPS, so then the given value will be divided by 60. So then the unit gets converted into RPS. So that you can represent it as N dash. So if you're writing N dash, you have to take the value of N and divide it by 60. If you're taking directly N, so then it will be in the RPM and not in RPS. So this is what you will get. So later you can simplify this little bit. You have 2 pi by 1000 something and all. So you can just simplify this numerical data. So in place of that, you can write 0.062, because you're taking 2 into pi. Pi value is 3.14 whole cube. So this entire value in the numerator divided by 1000 in the denominator, you will get this value 0.062. So after you simplify the constant value, so then you can write mu into n dash whole square divided by h. So this part of the elemental ring remains the same. You will write r to the power of 4 minus r naught to the power of 4. So this is the equation what we get. But here also it is in terminologies of R, but in data handbook it will be in terms of D. So we are changing that into D2 to the power of 4 minus D1 to the power of 4. So this is the derivation part for the power loss due to friction in an hydrostatic bearing. So this is how you have to derive the equation. They can just ask you derive the equation for load carrying capacity. Sometimes they can ask you to derive the equation for load carrying capacity and rate of oil flow. Or they can ask you to determine the derivation for load carrying capacity with the power loss and friction. So you should be able to derive properly. If you derive properly, so the marks assigned to you, you can get it easily. It is not like theoretical thing what you will be mugging and writing. So easily you can score. If you go wrong, usually you will lose marks also. So be careful to use proper equations and to give the necessary equations as asked in the examination or in the internals. So any doubt in derivation part until here?
No, no.
So you have to see that you will do properly. So after that, the numerical start basically. So I will, this part we have to solve, then only we will come to know how you will do it. So I will just explain you how the process will be. Tomorrow we will complete the numericals. So let us start with the first problem now. If it extends 5 more minutes also, let us solve one problem and leave. It is a simple one, no need to worry. So instead of giving hydrostatic step bearing, sometimes they can give you as hydrostatic thrust bearing also. Thrust is nothing but like the amount of load the bearing is withstanding, right? So you should not confuse that it is not hydrostatic step bearing or it is not hydrostatic bearing. It is being given as hydrostatic thrust bearing. It is one and the same. So the question is like this. Kindly take down the question, or else you can take the snapshot of it. Everyone take down the snapshot of it. Have you people taken down? Have you taken the snapshot of it?
Yes, ma'am.
Yeah. So now you see what is the specifications which are being given. So the thrust load is being given as 500 kilonewton. So this thrust load is nothing but the load which will be acting in the normal direction. So our W will be equal to 500 kilonewton. And then they have given the speed with which the shaft is rotating. So it is 720 rpm, which is nothing but N. But if you need the value of the speed with which the shaft is rotating in RPS, so then you have to divide 720 divided by 60. So then the unit gets changed to RPS. In that case, it is 720 divided by 60. It will come nearly to 12 RPS. So if you are using in RPS, kindly denote with another symbol. It is better to use as N dash. Okay. So this is a difference you should show when you are converting the unit from RPM to RPS. After that, it is given as the shaft diameter. This shaft diameter is nothing but the value of D2. And recess diameter will be given as 300 mm. So this we usually consider it as our D1. Apart from that, you are aware about the film thickness, which is represented by H, which has been given as 0.15. So this is the minimum oil film thickness what we considered for solving the problem. Along with this, you have to determine the viscosity of the lubricant. Sorry, viscosity of the lubricant is given already. So it is 29.3 centipoise. So this is the value for viscosity which is being given. So after all the specification details you are aware about, then you should see what needs to be calculated. So they have asked you to determine the supply pressure. So you have to use the pressure equation and determine the supply pressure. So then the flow requirement in the oil film. So that you have to determine. And lastly, what is the power loss? So we know the equation for power loss due to friction. So I'll be using that equation and you will solve the problem. So first one is the supply pressure. So supply pressure is nothing but the oil which has been passed through the inlet of the oil pipe, right? So that is represented usually by P naught. So you should be knowing what is the equation you have to use. If they say supply pressure, it is nothing but P naught. We have derived the equation for P naught. So you will use the equation, write it. So it is always 8W Please write down the equation, log of d2 by d1 divided by pi into d2 square minus d1 square. So you will substitute the value and tell me what is the answer you are getting. See, 8 will remain the same. The thrust load which has been subjected on the bearing is 500. So it is 500 kilonewton, not Newton. You have to multiply into 10 raised to 3. So 10 raised to 3 into log of both the diameter of the shaft and the recess has been given. So shaft diameter is 500 mm, which is D2. So in place of D2, you have to write in terms of meter. Don't go wrong. You have to convert that into meter. So it will be 0.5 divided by D1, which is the recess diameter. It is also given in terms of mm. Convert that into meter. So it will be zero point 0.3. Then divided by the denominator value. Pi is a constant. D2 is zero point 0.5, means 500 mm is converted into meter. So it is zero point 0.5 whole square minus D1 value was 300 mm. We have converted that into meter. So it is zero point 0.3 whole square. So kindly simplify and let me know what is the supply pressure value you are getting. You can either keep in terms of Newton per meter square or in megapascal. Kindly let me know what is the value you do get. Calculate and let me know. I will be taking the attendance.
Ma'am, same value.
Same answer, ma'am.
You are getting the same. You
Yes,
can
ma'am.
keep in both the units. So then we have the flow requirement. So we have derived the equation for flow requirement. You know this equation. We derived in terms of R upon R naught, but as per the data handbook, it is in terms of D2 and D1. Even in the numerical, it is given in terms of shaft diameter and recess diameter only. And hence, we will change the derived equation as per the data handbook. As per that, we have to use the flow requirement, which is nothing but our rate of flow. So if they ask you flow requirement, you should not confuse. The rate of flow equation is one and the same to determine the flow requirement. So you will use the same equation for rate of flow what we derived. So it will be pi p naught h cube divided by 6 mu into log of d2 by d1. You cannot determine the rate of flow without knowing the supply pressure, which is nothing but the P naught, right? So always, if they don't ask you to determine supply pressure also, you should determine the value of P naught. Then only you can determine the rate of flow. They can ask or they may not ask, but they will ask for sure the rate of flow. Indirectly to say that you need to determine P naught. So the very first step is to determine the value of P naught. So after that, now the rate of flow equation you have in this pi value, you know it is a constant. P naught right now you have calculated, which is 4.065 into 10 raised to 6, right? So you will substitute that value, and the film thickness, oil film thickness is given as 0.15 mm. Don't forget to convert that into meter, right? So this will be 0.15 into 10 raised to minus 3. And sometimes students forget to write whole cube. So please write whole cube. It is not only h, it is h cube divided by 6 into viscosity of the lubricant. It is given in centipoise. You have to convert that into Pascal second, 29.3 centipoise. So kindly convert that. It will be 29.3 into 10 raised to minus 3. And then log of d2 by d1. d2 value is given here.
Excuse me, ma'am.
Yeah.
Ma'am, few of us have a workshop today that starts at 10:30, ma'am.
Okay,
That's
fine.
organized
Which?
by the college. And we have some helicopter technology workshop today.
Fine, 2 minutes, 2 minutes. So you will just substitute this, and after that, you have to get this value. So power loss I will be taking in the next class. So until I take the attendance, you just calculate and let me know the value of Q, how much you get. I will take the attendance quickly.
0.99 into 10 power minus 4.
Okay, just let me take the attendance. Abdul Khalik Pasha. Abdul Khalik Pasha. Others, kindly type your name and USN in the chat room. Akhil KV. Akhil. Anil Kumar. Ankesh Aman. Gautam Krishna. Balaji VR.
Yes, ma'am.
Beldar Mohammed. Chaitanya.
Present, ma'am.
Chetan Kumar. Chetan is there. Dheeraj. Ishant.
Yes, ma'am.
Harshit.
Yes, ma'am.
Himanka.
Yes, ma'am. Present, ma'am.
Kanishka. Kanishka is not there. Nagamurali Krishna.
Yes, ma'am.
Kunal Raj. Kindly mute your mics, others. Danush. Mohammad Ayan. Mohammad Ayan.
Ma'am,
Mo-
Kunal wrote in chat box.
okay, I have given him the attendance. Mohammad Junaid.
Yes, ma'am.
Shri Prasad.
Yes, ma'am.
Niharika,
Yes, ma'am.
Okay.
Nihar Venkat Sai,
Yes, ma'am.
Nikhilar,
Yes, ma'am. Yes, ma'am.
Neerab,
Yes, ma'am.
Prajwal, Prajwal S. Bhatt,
Present, ma'am.
Rishabh Pandey,
Present, ma'am.
Roshan Yadav, Roshan, absent.
Present.
Present.
Yes, ma'am.
Rohan is there? Rohan Kaglakar?
No, ma'am, he's not there.
He is absent. Okay. Sumant Sagar? Sumant? Sagar Dutt Mathur?
Yes, ma'am.
Sagar GV?
Present, ma'am.
Okay. Sanjay Raghav?
Present, ma'am.
Shobit?
Present, ma'am.
Okay. Siddharth?
Present, ma'am.
Siddharth Sridhar? Siddharth Sridhar is absent. Subramanya?
Present, ma'am.
Subramanya? Okay.
Present, ma'am.
Yes, yes, yes. Tirumana Sethi Rohan? Rohan? Ullas? Ullas is not there. Vidyan?
Present, ma'am.
Varun?
Yes, ma'am.
Pavan?
Present, ma'am.
Danush? Danush?
Ma'am, present, ma'am.
Okay, okay, okay. Dhyanesh? Dhyanesh Kumar? Gunasagar?
Present, ma'am.
Meghanatha?
Present, ma'am.
Rasik Baran?
Present, ma'am.
Shiva Krishna? Shiva Krishna is absent. Shreya? Sorry, Shreyas. Absent. Srinivasalu?
Present, ma'am.
Yogananda? Yogananda is absent. Kiran?
Yes, ma'am.
Ranveer Singh Chauhan? Ranveer, he attended one class and again, don't know. Gautam Sai? Gautam Sai? Shiv Pavan? Alok? Alok is absent again, don't know why. Abdul Khalik Pasha?
Ma'am. Present.
Alok is there?
Yes, ma'am.
Why you were absent in the last class then?
I was present, ma'am. My
No,
mic doesn't
no.
work.
Okay. So in the last class you were there.
Yes, ma'am. I've been attending regularly.
Okay. So Abdul Khalik Pasha is not there. Fine. Everyone take care. Have a nice day. In tomorrow's class, we will be solving the problems. Do attend the class in the second hour again from 9:30 to 10:30. So until then, take care. Have a nice day.
Ma'am,
Yes,
59, ma'am, Rohan.
Rohan.
I got logged out by mistake, ma'am, just at that time.
How come you can do that?
No, like by mistake, I don't know, because of some network problem. I
Okay,
logged.
I have given the attendance. Okay.
Yes.
Yeah. Okay, then take care. Bye bye.
Thank you, ma'am.
Yeah.